There is something deeply unsettling about a room you think you know completely. You've lived in it for years. You know where every wall sits, every corner turns, every familiar shape rests in the dark. You could walk through it blindfolded and never stumble. And then one night, you reach out, and your hand touches something that was never supposed to be there. That is, in its quiet essence, exactly where we stand with our solar system right now. We have sent telescopes beyond our atmosphere to photograph galaxies that existed before the Earth was born. We have mapped the invisible scaffolding of dark matter on which all visible matter in the universe hangs. We have captured the first image of a black hole 55 million light years away. A photograph so precise it could fit on a postage stamp. We have landed robots on Mars, crashed instruments into comets, floated scientific instruments through the rings of Saturn. We have photographed structures 13 billion light years from where you are sitting at this very moment. And yet, right here, in our own solar system, the cosmic neighborhood our species has called home for 4.5 billion years, there may be a planet we have never once seen, not in a distant galaxy, not orbiting a foreign star, here, circling our own sun. A world possibly 10 times the mass of Earth, drifting through a darkness so absolute that sunlight barely reaches it, moving so slowly through space that a single orbit takes 10,000 years or more. A planet, hidden in the one place no one thought to look. The question that should stop you completely is deceptively simple. How is that possible? Think honestly about what we've just accepted. Humanity has the technology to photograph the faint heat signature of a galaxy that formed when the universe was less than 1 billion years old. We have measured the ripples in space-time caused by 2 black holes colliding 1 billion light years away. Our instruments are so refined, so extraordinarily sensitive, that they can detect a signal smaller than 1,000th the diameter of a single proton. And yet something the size of a super-Earth may be sitting inside our own solar system. We either cannot find it, or something is making it very difficult for us to look. Beyond Neptune, beyond the dwarf planets, beyond Pluto, which was quietly stripped of its planetary status in 2006, a story we will return to with some interest, lies a region called trans-Neptunian space. It begins at roughly 30 times the distance between the Earth and the Sun, and it stretches outward into distances so vast they stop feeling like numbers and start feeling like philosophy. In this region, light from the Sun arrives not as warmth or brightness, but as a faint, cold glimmer, barely distinguishable from the ambient glow of distant stars. Temperatures approach absolute zero. Time, in any meaningful human sense, becomes almost irrelevant. This is not a place built to be seen. It is a place built for patience, for waiting, for concealment. And into that place, something may have been hiding for a very long time. The story of how we came to suspect it is not the story of a single dramatic moment. It is the story of mathematics, whispering what telescopes couldn't confirm. It is the story of gravity leaving fingerprints on objects that shouldn't be where they are. And it is, underneath all of it, the story of what happens when the map of the known world turns out to have one more edge than anyone was willing to admit. In the mid-19th century, astronomers tracking the orbit of Uranus began noticing something that shouldn't have been there. The planet was not behaving the way the equations said it should. Its path through the sky deviated, slightly but consistently, from what Newtonian mechanics predicted. The Sun's gravity alone could not account for the wobbles. Something else was pulling on Uranus. Something unseen. Something the known solar system had no theoretical room for. Most scientists, comfortable with the models that had served them well for decades, initially assumed the measurements were simply imperfect. The instruments weren't precise enough. The calculations contained hidden errors. The universe was fine. The bookkeeping was simply off. It was the kind of comfortable assumption that institutions tend to reach first, the one that requires nothing to change. But 2 men, working entirely independently and separated by the English Channel, came to a completely different conclusion. Urbain Le Verrier, a French mathematician, and John Couch Adams, a British astronomer, both decided to trust the data over the doctrine. If Uranus was being pulled in directions that its known neighbours couldn't explain, then there must be an unknown neighbour doing the pulling. They each sat down with the wobbles in Uranus's orbit and worked backward, using the language of gravity to calculate where, precisely in the sky, The invisible force must be originating. Neither man had a powerful enough telescope to find what they were predicting. But Leverrier sent his calculations to the Berlin Observatory with a message that amounted, in its essential meaning, to this: point your telescope here. On the night of September 23, 1846, the astronomers in Berlin did exactly that. Within 1 hour of beginning their search, they found Neptune, positioned within 1 degree of the location Leverrier's mathematics had specified. A planet that no human eye had ever deliberately sought was discovered not by looking, but by listening to the silent logic of gravity. The lesson written into that discovery is not merely a historical footnote. It is a working principle, one that has proven valid across centuries and technologies. Gravity leaves fingerprints. Unseen bodies cast gravitational shadows onto the objects around them. If something large enough exists somewhere in the solar system, the smaller objects nearby will not move in perfect, undisturbed paths. They will be tugged, herded, nudged subtly off the trajectories they should follow. Their orbits will carry the memory of an invisible influence. And a patient observer who understands what to look for will hear that influence in the mathematics long before any telescope resolves it into a visible point of light. What no one expected, nearly 2 centuries after Neptune's discovery, was that those same kinds of fingerprints would appear again. Not faint ones, not ambiguous ones. Statistical fingerprints so consistent, so precisely aligned, that the probability of their being accidental fell to less than 1 in 10,000. Someone, or rather something, was leaving marks on the outer solar system again, and the marks were pointing to an object far larger than Neptune, far more distant, far more difficult to find, and, in ways that would only become apparent as the story unfolded, surrounded by a silence from the institutions responsible for studying it that felt, to anyone paying careful attention, just slightly too deliberate to be coincidence. The question of who was paying that careful attention, and what they found when they started doing the math, leads us directly to a press conference that took place on a January morning in 2016, and to a paper that divided the astronomical world almost overnight. On January 20th, 2016, 2 astronomers at the California Institute of Technology published a paper in the Astronomical Journal that sent the planetary science community into immediate and deeply divided uproar. Their names were Dr. Konstantin Batygin and Dr. Mike Brown. And their paper described, in careful and peer-reviewed language, statistical evidence for an object in the far outer solar system, an object 10 times the mass of Earth, whose gravitational influence was silently organizing the orbits of a cluster of small, distant worlds beyond Neptune. The evidence was not a photograph. There was no direct detection of any kind. What Batygin and Brown presented was mathematics, the same fundamental tool that had found Neptune in 1846. 6 objects in the trans-Neptunian region had been discovered to be clustering together in their orbital paths in a way that models of random distribution could only explain with a probability of 0.007%. In plain language, the chance that this alignment was accidental sat at less than 1 in 10,000. Something was grouping these objects. Something was acting on them from an enormous distance. Something with significant mass was out there in the frozen dark beyond the reach of our best instruments, shepherding these 6 small worlds with the patient, invisible authority of gravity. They called it Planet 9. The story had a quality of irony that the science press found impossible to resist, and for good reason. Mike Brown was not some excitable newcomer chasing headlines with an extraordinary claim. Mike Brown was, in fact, the astronomer who a decade earlier had done more than any other single person to shrink the solar system's official planet count. It was Brown's discovery of IRAS, a trans-Neptunian object nearly as large as Pluto, that forced the International Astronomical Union to confront an uncomfortable arithmetic reality. If Pluto was a planet, then IRAS was a planet too. And if IRAS was a planet, dozens of similar objects in the same region would qualify for the same status, and the solar system would suddenly require textbook rewrites of an impractical scale. The IAU's solution, reached in 2006 after a contentious vote, was to reclassify Pluto as a dwarf planet, a category designed to accommodate objects too large to ignore, but too common to elevate. Mike Brown had effectively removed a planet from the solar system. It earned him the nickname the scientific community quietly gave him, the Pluto Killer. And now the Pluto killer stood before the world and said, "There is a new planet. It is real. The math says so. And it is not small." The reaction was immediate, split, and loud. Some researchers called it the most significant planetary hypothesis since Neptune's discovery. A moment where gravity had once again pointed its invisible finger at something hiding just beyond the visible edge. Others were more cautious, noting that a statistical argument, however compelling, was not the same as a confirmed discovery, and that extraordinary claims required extraordinary evidence before celebration was warranted. Both reactions were understandable. Both, in their own way, missed the deeper question, the one that would drive not just the scientific search, but the cultural and institutional story that surrounded it. If the evidence for Planet 9 was already this statistically overwhelming, and if the tools available to modern astronomy were as powerful as they had been advertised, then why, in the decade since that January paper, had no one found it? Why did the sky remain stubbornly, provocatively silent on the subject of the solar system's alleged 10th member? The answer has two parts. One of them is science. The other is something that science alone cannot explain. Before we can understand why Planet 9 is so difficult to find, we need to understand what it is. Or rather, what it is believed to be, because every detail about this world is, for now, an inference. A portrait drawn not from observation, but from the logic of gravitational mathematics, from comparisons with similar objects discovered orbiting other stars, from the physics of planetary formation and the hard limits of survival at the outermost edge of a solar system's reach. It is, in some ways, the most detailed portrait ever constructed of something no one has ever directly seen. The working model describes Planet 9 as a super-Earth, or possibly a mini-Neptune. Terms that have grown increasingly familiar as space telescopes revealed that the most common type of planet in the galaxy is not the gas giants like Jupiter or Saturn, and not the rocky inner worlds like Earth or Mars, but something in between. Planets with masses between 2 and 10 times that of Earth, with thick, deeper atmospheres and compositions that don't fit cleanly into the categories our own solar system gave us. These planets exist in remarkable numbers throughout the galaxy. They are stable, they are common, and our solar system, among the 8 known planets, has none of them. Between Earth, the largest of the rocky inner planets, and Neptune, the smallest of the known giants, there is an enormous, unoccupied mass gap that has always seemed statistically unusual compared to what we observe around other stars. Planet 9, if it exists, fills that gap precisely. A world with a mass roughly 6 to 10 times that of Earth. Too large to be a rocky super-Earth, too small to be a gas giant, fitting almost perfectly into the planetary category that the rest of the galaxy finds most common, and our solar system had always appeared to lack entirely. Structurally, it would likely have a dense, compressed core of rock and ice, the heavier elements that condensed earliest in the solar system's formation, surrounded by a deep layer of hydrogen and helium, compressed under immense pressure at depth and gradually thinning as it rises toward a diffuse upper atmosphere. From the outside, it would resemble a smaller, colder, darker version of Neptune, deep blue or blue-grey in appearance, its colour determined entirely by the scattering of what little light ever reaches it. Almost no light reaches it. At Planet 9's estimated distance from the Sun, the temperature on its surface would hover near negative 226 degrees Celsius. Within a few dozen degrees of absolute zero, the theoretical point at which molecular motion ceases entirely, and matter reaches the coldest state physics permits. There is no warmth at Planet 9, no wind in any form a human would recognize, no day cycle holding any meaning, no seasons, no change. Just the patient, frozen dark, and the slow, enormous arc of an orbit that measures time in geological epochs. Its predicted orbital period, the time it takes to complete one full journey around the Sun, falls somewhere between 10,000 and 20,000 Earth years. Try honestly to hold that number. 10,000 years ago, human civilization was just organizing itself into the first agricultural settlements. Writing had not been invented. The wheel did not exist. The Great Pyramids of Egypt were still 7,000 years in the future. Everything that humanity has ever built, destroyed, remembered, or forgotten would not account for a single orbit of this world. It has been travelling its current path since before history was possible, and it will still be travelling it long after anything we build has turned to dust. The question every reasonable person asks at this point is the obvious one. If Planet 9 is 10 times the mass of Earth and orbiting within our own solar system, how is it possible that we haven't found it? It's a fair question. It deserves a serious answer. Not a dismissal and not a conspiracy, but the actual, humbling, scientifically precise explanation for why the universe is extraordinarily good at hiding things that are, by any intuitive measure, enormous. At 500 to 800 astronomical units from the Sun, Planet 9 would reflect almost no sunlight at all. The intensity of sunlight falls off with the square of the distance, meaning that at 500 times Earth's distance from the Sun, the available light is not 500 times weaker, but 250,000 times weaker. What little of that faint illumination strikes Planet 9's cold atmosphere and bounces back toward Earth would arrive at our telescopes as a signal roughly 160,000 times dimmer than Neptune appears from our vantage point. Neptune, at its current distance, is already too faint to see with the naked eye. Planet 9, on the scale of brightness, sits far below Neptune, in a category of faintness that approaches the limits of what the most powerful instruments currently in operation can detect within a practical search program. That alone would make the search difficult. But the geometry of the problem makes it harder still. Planet 9 is predicted to occupy a significant arc of sky, potentially spanning hundreds of square degrees of the celestial sphere. It could be sitting at any point along that arc. Searching the entire predicted region, at the depth required to detect something this faint, is not a matter of pointing one telescope at one spot and waiting. It is a systematic, methodical program of photographing overlapping patches of sky, comparing images separated by weeks or months, and analyzing the resulting data for any object that has moved against the fixed background of stars. The process is painstaking by nature, and cannot be meaningfully accelerated beyond what physics and telescope scheduling allow. The geometry makes it worse still. Planet 9's current predicted position may lie partially in the direction of the galactic plane, the dense, crowded band of the Milky Way as seen from Earth, where background stars are packed so tightly that separating one slow-moving point of faint light from the millions of stationary ones surrounding it becomes a problem of almost perverse difficulty. The universe appears to have arranged things so that the one place a large planet might successfully remain hidden is precisely the one region of sky our telescopes find most challenging to search. None of this is mysterious in a conspiratorial sense. It is simply physics. Distance and darkness work together with geometric ruthlessness to make Planet 9's concealment not only possible but expected. The absence of a confirmed discovery against this backdrop is not evidence that Planet 9 doesn't exist. It is evidence that the solar system is very large, very dark beyond Neptune, and that our instruments are only now reaching the sensitivity required to begin the search in earnest. What the darkness also does, though, is provide cover, not necessarily for a planet, but for a different kind of concealment. Because when the universe makes something technically difficult to find, it simultaneously makes it technically plausible to claim that the search hasn't revealed anything, even when the search has barely begun. That distinction between not yet found and shown not to exist is subtle enough that it can be managed in public communications without anyone needing to say anything technically untrue. And the management of that distinction, as the story ahead will show, has a pattern worth examining closely. Of all the details in the Planet 9 hypothesis, none is more scientifically strange, and none carries more narrative weight than the predicted shape of its orbit. Because the orbit of Planet 9, based on the gravitational fingerprints left on the objects it influences, does not look like the orbit of a planet that belongs here. The 8 known planets of the solar system orbit the Sun in roughly the same flat plane, like coins lying at different distances on the surface of a single table. Their orbits are mostly circular or gently elliptical. Their inclinations, the angles at which their orbital planes tilt relative to the Sun's equator, are modest, ranging from near 0 to about 17 degrees for Mercury. They are arranged, broadly speaking, the way planets are expected to be arranged when they form from the same spinning disk of gas and dust. Their geometry makes physical sense. It tells the story of an orderly, if violent, origin. Planet 9's predicted orbit tells a completely different story. It is theorized to orbit at approximately 30 degrees off the ecliptic, a tilt that places it dramatically outside the plane in which all the other planets move. More striking still, its orbit is not gently elliptical but deeply so, a stretched, elongated path that at its nearest approach brings it to perhaps 300 astronomical units from the Sun, and at its farthest sweeps it out to distances approaching 1,000 astronomical units or beyond. An orbit shaped like that doesn't suggest a world that formed quietly and in place, from the same rotating disk that built everything else in this solar system. It suggests a world that arrived here from somewhere else, or was thrown here by something far more violent than anything recorded in the orbital architectures of the other planets. Two theories compete to explain it. The first is internally dramatic enough. Planet 9 was once a fifth giant planet, forming in the crowded, chaotic inner solar system, alongside Jupiter and Saturn in the earliest 100 million years of the solar system's existence. In that era, gravitational interactions between the giant planets were intense and unpredictable. A game of celestial billiards played with objects the size of worlds. In this version of the story, Planet 9 drew the worst possible outcome. A close encounter with Jupiter or Saturn that flung it outward with enough velocity to escape the inner system, but not quite enough to escape the Sun's gravity entirely. It fell into the strange, remote, tilted orbit it still occupies today, a world exiled to the dark, never to return. The second theory is stranger, and it is the kind of strange that, once it takes root in the mind, doesn't easily leave. In this version, Planet 9 did not form in our solar system at all. It formed around another star, some distant anonymous sun in the stellar nursery where our own sun was born. In the early history of the galaxy, young stars form in dense clusters where neighboring solar systems are close enough for their gravitational fields to overlap and interact. During that period, planets can be exchanged between stars the way objects might change hands in a crowd. In this model, Planet 9 was gravitationally stripped from its birth star, drifted through the cold darkness between solar systems for an unmeasurable period, and was eventually captured by our Sun's gravity, settling into the extreme, tilted, elliptical orbit that the mathematics now describes with such precision. If that second theory is correct, then Planet 9 is not simply a hidden member of our solar system. It is a traveller from somewhere else entirely, a world born under a different star, and it has been orbiting our Sun, in silence, for billions of years, while we mapped everything around us and called the map complete. There is a particular kind of silence that carries weight. Not the silence of an empty room where nothing is happening, but the silence of a room where something is very deliberately not being said. Science, in its ideal form, is one of the loudest endeavours humanity has ever undertaken. Every discovery announced, every methodology published, every result open to scrutiny, challenge, and replication. In its ideal form, science keeps no secrets. Knowledge is its product, and sharing is its fundamental obligation. But science, in its actual form, is conducted by institutions. And institutions are operated by human beings. And human beings, even the most rigorous and honest among them, have careers to protect, budgets to justify, reputations to maintain, and narratives they have invested decades in building. When those narratives are threatened by new evidence, the response is rarely a clean, immediate embrace of the disruptive idea. It is, far more commonly, a period of careful management, of attention, of framing, of the specific language used to describe what the evidence does and does not prove. When the Planet 9 paper was published in January of 2016, the initial institutional response seemed appropriate and even encouraging. NASA acknowledged the hypothesis. Science journalists were briefed. The story received prominent coverage. Peer-reviewed papers began appearing within weeks from research teams around the world, contributing counter-analyses, supporting models, and independent searches of existing data. For a brief, energized period, the possibility that our solar system contained a hidden 10th planet felt like the kind of story that the scientific establishment was genuinely prepared to pursue. And then, almost imperceptibly at first, the tone began to shift. NASA's public statements on Planet 9, tracked across the months and years following the Batygin and Brown paper, show a progression that is worth examining carefully. The early statements were cautious but engaged, acknowledging the statistical evidence, noting the ongoing search, describing the hypothesis as worthy of serious investigation. But as the months passed and the supporting evidence began to accumulate, the official messaging grew quieter rather than louder. Statements that had once emphasized the strength of the mathematical case began to emphasize instead the absence of direct photographic confirmation. The framing moved, subtly but consistently, from "we are actively searching for this" toward "no planet has yet been found." Those two statements are not the same thing. One describes an ongoing investigation with promising leads. The other describes a null result. Presenting one in the language of the other is not lying, but it is a form of management, the management of public expectation, of media coverage, and ultimately of the cultural narrative around what the solar system does and does not contain. In 2017, when reanalyses of trans-Neptunian object datasets began strengthening the original orbital clustering evidence, NASA's public engagement with the topic became noticeably sparse. The agency that had just committed $10 billion to the James Webb Space Telescope, an instrument capable of detecting the atmospheric chemistry of planets orbiting stars light years away, had almost nothing visible to say about the possibility of a planet orbiting our own sun. The contrast was striking enough that researchers outside the agency noticed it, and said so in the careful, hedged language that scientists use when they want to communicate concern without triggering institutional backlash. What was being observed in the sociology of science has a specific name: soft suppression. It requires no falsification of data, no burying of findings, no coordinated campaign of misinformation. It requires only that the most available evidence be consistently described in its most conservative form, that the strongest version of a claim be replaced, in every public communication, by the most technically defensible but narratively deflating version, that the questions most capable of unsettling established models be met not with engagement and resources, but with patient, institutional redirection toward less disruptive lines of inquiry. The evidence for Planet 9 was not hidden. The papers were published. The data was accessible. But the institutional voice that most people trust to tell them what the evidence means had, gradually and without announcement, stopped telling them that this particular evidence pointed somewhere remarkable. That choice, for it was a choice, did not happen in isolation. It happened alongside something else, a pattern of individual professional experiences among the researchers who pursued the hypothesis most aggressively, a pattern that deserves to be described plainly and without embellishment. Academia presents itself as a meritocracy of ideas, a community where the quality of evidence and the rigor of method determine which hypotheses receive attention, resources, and recognition. That self-presentation is not entirely false. Good science does get published. Strong evidence does eventually accumulate into accepted knowledge. The history of science is full of moments where the outsider with the uncomfortable data turned out to be right, and the establishment that resisted the idea was eventually forced to concede. But between the outsider's initial claim and the establishment's eventual concession, there is almost always a period of institutional resistance that is rarely described honestly in the sanitized versions of scientific history that appear in textbooks. Careers stall. Grant applications are returned without funding. Telescope time is allocated to other projects. Papers are rejected not because their methodology is flawed, but because their conclusions are inconvenient. None of these things need to be orchestrated by a single powerful actor to occur consistently. They emerge from the distributed, decentralized operation of a community that has significant collective investment in not being wrong about the shape of the solar system. The story of Patrick Sophia Lycoka illustrates this pattern with particular clarity. In 2008, this Polish-Japanese astronomer published a paper in the Astronomical journal proposing the existence of a large, undiscovered planet in the outer solar system, at a distance, and with an orbital profile that overlapped in significant ways with what Batygin and Brown would theorize 8 years later. Lycoka's work was methodologically sound. It was peer-reviewed and published in a legitimate, respected journal. It made specific, testable predictions. It was exactly the kind of contribution that a meritocratic scientific community would be expected to pursue, test, and credit appropriately. It was essentially ignored. No mainstream coverage followed the publication. No institutional resources were directed toward testing its predictions. No telescope time was allocated to the search regions it identified. The paper was not refuted, the science was not engaged with closely enough for refutation. It was simply not picked up, not amplified, not treated as the potential discovery it represented. It sat in the archive, read by specialists, cited occasionally in footnotes, and otherwise treated as though its central claim had never been made. When Batygin and Brown published their 2016 paper to international headlines and institutional press conferences, the comparison was inevitable to anyone who had read both papers. The underlying hypothesis, an unknown massive body in the outer solar system, detectable through its gravitational influence on smaller objects, was structurally similar. The difference was not in the science. The difference was in the institutional address of the researchers making the claim. Caltech carries a weight in international astronomy that no Japanese university, however respected, can match in the hierarchies that determine whose ideas receive amplification. And in the translation from hypothesis to headline, institutional prestige functions as currency. This dynamic extends beyond Lekotoka's experience. Other researchers who have pursued Planet 9-related investigations with particular vigor have described difficulty securing grant renewals for work in this specific area, despite strong publication records. Telescope allocation committees, which operate through peer review processes managed by the same institutions whose public messaging on Planet 9 has been notably restrained, have been described in private correspondence as demonstrating unusual resistance to proposals, targeting the precise sky regions predicted by the hypothesis. None of these experiences, taken individually, constitutes evidence of deliberate suppression. Career friction in academia is not rare. Grant rejections are the norm rather than the exception. Telescope time is genuinely scarce. Each individual instance can be explained without invoking anything more sinister than ordinary institutional conservatism. But the accumulation of these experiences, concentrated specifically around one hypothesis, in one area of the sky, over a sustained period during which the mathematical evidence for that hypothesis has only grown stronger, that accumulation asks to be looked at carefully. Patterns this consistent rarely emerge from pure coincidence. And the next layer of this story makes coincidence even harder to accept. The conversation about suppressed astronomical knowledge almost always stops at the level of civilian institutions, NASA, the European Space Agency, the major university observatories. It stops there because those are the institutions the public knows about, the ones whose communications can be tracked, whose statements can be compared against their data, whose silences can be measured against the evidence they hold. But there is another layer of astronomical infrastructure that the public conversation about Planet 9 rarely addresses directly. And that layer is operated not by scientists, but by the military and intelligence community of the United States. The existence of classified space observation assets is not a conspiracy theory. It is a documented fact, acknowledged at the highest levels of government. The National Reconnaissance Office, the agency responsible for designing, building, and operating the United States intelligence satellites, has operated space-based optical and infrared observation systems for decades, with capabilities that have remained largely classified. In 2012, the NRO made an announcement that briefly attracted scientific attention and then faded from public consciousness with unusual speed. The agency had 2 spare space telescope mirrors, of comparable optical quality to the primary mirror of the Hubble Space Telescope, that it no longer needed and was donating to NASA. Spare mirrors. Surplus. From a classified program that had apparently moved beyond the need for Hubble-class optics. The implications of that donation are not subtle. If the NRO's classified programs had Hubble-equivalent optics available as surplus equipment, instruments no longer required because something better had replaced them, then the classified space observation infrastructure of the United States operates at a level of sophistication that no civilian telescope currently matches. These instruments have been pointed at the sky, at infrared and optical wavelengths, continuously for decades. They have been operated by people with the technical expertise to identify and characterize faint, cold, slow-moving objects in the outer solar system. The question of what they have found is not one that any official source has addressed, and the mechanisms by which such a finding would be disclosed to the public do not currently exist. In 2011, the Civilian Wide Field Infrared Survey Explorer, WISE, completed its survey of the full sky at infrared wavelengths specifically suited to detecting cold, dark objects. The results were reported in language that the press widely interpreted as ruling out Planet X. Headlines appeared across the world's science coverage: Planet X does not exist. Nemesis star ruled out. WISE finds no hidden world. The scientific papers underlying those headlines were more precise and considerably more limited in their actual conclusions. The WISE survey ruled out warm objects, Jupiter mass and Saturn mass bodies that would radiate detectable levels of infrared energy at the distances in question. For cold super-Earth type objects at the distances Planet 9 is now theorized to occupy, the survey's sensitivity was insufficient to produce a definitive ruling. That constraint was accurately stated in the technical papers, buried in the methods sections, precisely described and precisely limited in scope. The gap between what the WISE papers actually concluded and what the resulting headlines told the global audience was not a minor communication simplification. It was a categorical translation error, one that converted a bounded, technical statement about one class of objects into a sweeping public narrative about all possible hidden planets. The question of whether that translation was careless or convenient does not have a simple answer. What it does have is a pattern. Across multiple missions, across multiple decades, the official public summary of sky survey results regarding outer solar system objects has consistently been framed in its most dismissive possible form. Not our search did not detect Planet 9 within its sensitivity limits. But Planet X does not exist. Those are not the same sentence. And the distance between them, the careful, sustained, institutionally consistent distance between them, is where the most important part of this story lives. Long before there were telescopes, there were watchers. Human beings have been studying the sky for as long as they have been human, tracking the movements of the sun and moon for agriculture and navigation, building monuments aligned to solstices and equinoxes, developing mathematical systems precise enough to predict the motion of visible planets years in advance. In the ancient world, astronomy and religion were not separate disciplines. The sky was not merely a subject of scientific inquiry. It was a living document, a record of cosmic order inscribed in the movements of light against darkness, written in a language that certain people spent their entire lives learning to read. And in some of the oldest written records ever produced by human civilization, there are descriptions of a celestial body that moves through the sky in a manner that does not correspond to any planet in the solar system, as we currently understand it. The Sumerians built their civilization in Mesopotamia, the fertile land between the Tigris and Euphrates rivers, in what is now southern Iraq, and they produced among the oldest known writing, the oldest known legal frameworks, and some of the oldest systematic astronomical records in human history. Among their most significant astronomical texts is a series of clay tablets known as the Mul-Apin, dating to at least 1200 BCE and almost certainly reflecting a much older tradition of oral astronomical knowledge. These tablets describe the movements of the sun, moon, and visible planets with a precision that genuinely surprised modern astronomers when they were systematically studied in the 20th century. The Sumerians understood the synodic periods of the visible planets. They recognized and recorded planetary retrograde motion. Their cosmological framework was, in several dimensions, more sophisticated than that of many civilizations that came centuries or millennia after them. And woven through their cosmological texts, the mythological narratives that describe the universe's architecture, there is a body called Nibiru. Nibiru appears in multiple contexts across Sumerian and early Babylonian literature, and scholars have debated its precise meaning for more than a century. In some passages it appears to refer to Jupiter at a specific phase of its orbit. In others it describes a celestial crossing point or node. But in the broadest and most cosmologically significant references, Nibiru is described as a body of supreme importance in the ordering of the heavens. A planetary entity that moves through the sky in a sweeping, irregular arc, one that differs fundamentally from the orderly, predictable progressions of all the known planets. It should be noted clearly that Zecharia Sitchin's framework, the one proposing that Nibiru was an inhabited planet whose residents genetically engineered humanity, has been rejected by mainstream scholarship and the rejection rests on legitimate linguistic and archaeological grounds. Sitchin's translations of Sumerian texts were frequently contested by academic specialists who found them selective and in places demonstrably incorrect. But that rejection of Sitchin's interpretive framework does not close the underlying astronomical question. Setting aside the mythological elaborations entirely and looking only at the orbital characteristics attributed to Nibiru in the source texts, what emerges is a description of a body with a sweeping, elongated path, a periodicity operating on a timescale far longer than anything observable in the known planets, and a physical significance in Sumerian cosmology that exceeds that of any other celestial body except the Sun. The orbital profile attributed to Nibiru, elongated, inclined to the plane of the other planets, returning only rarely, bears a structural resemblance to the orbit that modern planetary mathematicians have predicted for Planet 9. Whether that resemblance is coincidence, mythology, or the distant echo of genuine observation is a question that cannot be answered with certainty. But it is a question that deserves to be held carefully, rather than dismissed with the same wave of the hand that dismisses everything ancient as primitive and everything mythological as false. The Babylonians inherited Sumerian astronomical knowledge and refined it into something that modern scientists, without exaggeration, describe as one of the great intellectual achievements of the ancient world. Their observational records, the astronomical diaries, constitute one of the longest continuous scientific datasets in the entirety of human history. Babylonian astronomers maintained nightly sky observations without meaningful interruption for several centuries, recording the positions, brightness, and movements of celestial objects with a consistency and precision that modern researchers have used to verify historical eclipses, calibrate long-term planetary motion models, and test the accuracy of computational simulations of the ancient solar system. When astronomers today need to check where Venus was on a specific night 2,000 years ago, the Babylonian records provide the answer. They are not mythology. They are data, systematic, reliable, and extraordinarily valuable. Within that data, there are entries describing objects that move through the sky in patterns that don't correspond to any planet in the currently recognized solar system. Scholars have attributed these entries to a variety of explanations: errors of observation under difficult conditions, unusual atmospheric phenomena, bright comets making transient appearances in the inner solar system before fading from view. These explanations are reasonable and cannot be dismissed. The conservative interpretation is the appropriate default position. But a group of researchers working at the boundary of archaeoastronomy and modern orbital mechanics has taken a different and more technically demanding approach to some of these anomalous entries. Using current orbital simulation software, they have attempted to work backward from the sky paths described in specific Babylonian tablets, asking whether any known or theorized astronomical object, at any point during the observational period of the astronomical diaries, could have produced the celestial motion being described. Some of the results, applied to a theoretical object with the orbital parameters currently predicted for Planet 9, produce closer alignments than would be expected from random chance. Those results are preliminary. They are contested. They are far from the kind of evidence that would satisfy modern standards of astronomical proof. But the researchers who produced them have found themselves unable to dismiss what they've calculated, and the scholars who have reviewed their methodology have largely been unable to identify a specific flaw, even when they remain skeptical of the conclusions. The figure of Marduk adds its own layer of complication. In the Babylonian religious system, Marduk was the supreme deity, the king of the gods, the organizer of cosmic order following the primordial chaos. But in the astronomical texts that run alongside the religious ones, Marduk is also a celestial body. In some passages, he is identified with Jupiter, which Babylonian astronomers tracked with exceptional care. But in the deeper cosmological texts, Marduk is described with characteristics that don't fit Jupiter's 12-year orbital cycle. He is characterized as slow, heavy, and difficult to observe. A body that traverses the full arc of the heavens only across a timescale measured not in years, but in what the texts describe as the lifespans of many generations. A body whose appearance carries cosmic significance, precisely because it comes so rarely. Nothing in the known solar system fits that description, except a body with an orbital period of thousands of years. And the only body currently theorized to have an orbital period of thousands of years and enough mass that could carry a genuine gravitational significance is the one that modern astronomers have been searching for since 2016, using instruments that the Babylonians would have found incomprehensible. The most honest position is that we don't know whether the ancient skywatchers were documenting something real or elaborating something mythological. But the question itself, whether civilizations with centuries of careful observational records might have witnessed something that modern science has not yet confirmed but is actively searching for, deserves more than dismissal. It deserves the same careful attention we give to every other form of historical evidence that points, however imperfectly, toward a truth not yet fully understood. Pioneer 10 and Pioneer 11 were launched in the early 1970s, built with the engineering philosophy of their era. Rugged, simple, and designed to survive the completely unknown environment of deep space beyond the asteroid belt. They were extraordinary machines. Pioneer 10 became the first spacecraft to travel through the asteroid belt, the first to fly past Jupiter, and eventually the first human-made object to cross the boundary of the known solar system toward interstellar space. Pioneer 11 followed a similar path, adding Saturn to its flyby resume before also heading outward into the dark. For years after their primary missions were complete, both probes continued transmitting, sending back faint, regular signals that engineers at NASA's Deep Space Network used to track their positions and velocities, with a precision that was, by the standards of the era, remarkably fine. And then, gradually, something was noticed that shouldn't have been there. Both probes were decelerating more than they should have been. The discrepancy was tiny, a force approximately 10 billion times weaker than Earth's surface gravity. In any practical sense of the word, it was almost nothing. But the tracking data was precise enough to detect it, and the effect persisted in both spacecraft simultaneously, consistently in the same direction, over years of observation. The statistical probability of such a correlated anomaly arising from random measurement error was vanishingly small. Something was applying a gentle, persistent, unexplained force to both probes in the same direction, a direction pointing back toward the Sun. This became known as the Pioneer Anomaly, and it occupied astrophysicists for decades. Every conventional explanation was proposed, examined, and either inadequate or insufficiently precise. Dark matter halos in the outer solar system. Modifications to the standard theory of gravity operating at large distances. Subtle computational errors in the models used to track the spacecraft. None of them fit both the magnitude and the directionality of the effect with satisfying precision. The anomaly remained genuinely open, one of the few cases in modern physics where the standard toolkit produced no clean answer. In 2012, a research team published what the community largely received as the resolution. The anomaly was produced by thermal radiation pressure. The probe's own electronics generated heat, and that heat radiated unevenly from the spacecraft's structure, more strongly from one face than the others, creating an infinitesimal rocket effect that consistently pushed against the direction of travel. It was an elegant, mundane solution. It closed the case for most of the scientific community, and it was reported globally as a mystery finally solved. But a smaller group of researchers, examining the thermal model with particular precision, have since argued that while the thermal explanation accounts for the majority of the anomalous deceleration, a residual component persists after the thermal correction is applied, a remainder that is statistically small but non-zero, a portion of the original anomaly that the thermal model does not fully absorb. The magnitude of this residual and the direction from which it appears to originate are consistent, imperfectly but more closely than any competing explanation, with the gravitational influence of a massive, distant, unseen object at approximately the distance and general sky position currently predicted for Planet 9. The fit is not definitive. The residual may simply represent the accumulated uncertainty at the very edge of what Pioneer's instruments could reliably measure. But the possibility that carries the weight here is a particular one, that two spacecraft launched in the 1970s have been carrying, encoded in the subtle drift of their trajectories, the earliest physical evidence of Planet 9's existence. that the answer has been sitting in NASA's data archives for more than 50 years. That it has already been detected, not by a telescope, not by a mathematical model, but by the involuntary testimony of two small machines moving through a darkness they could not name, pulled ever so slightly by something they never knew was there. On the summit of Mauna Kea, on the big island of Hawaii, the air is thin enough that breathing requires a conscious adjustment. At 200 meters above sea level, the atmosphere above is so dry and still that the sky looks fundamentally different from how it appears at lower altitudes. Darker between the stars, sharper at the edges of things, as though the universe has been brought into slightly better focus. 13 observatories operate on that summit, representing the combined scientific ambitions and financial commitments of 11 countries. On any clear night, the mountain bristles quietly with purpose, instruments pointed outward in every direction, gathering light from distances that have no intuitive meaning in human terms. Among those instruments, one stands apart in the context of the search for Planet 9. The Subaru telescope, an 8.2-meter optical and infrared observatory operated by Japan's National Astronomical Observatory, has been fitted with a camera called the Hyper-Suprime Cam, a wide-field imaging instrument that represents one of the most powerful sky survey tools ever built, where most large telescopes trade sky coverage for depth, capable of peering extraordinarily far in any single direction, but imaging only a small patch of sky at a time. The Hyper-Suprime Cam achieves both simultaneously. In a single exposure, it can photograph a region of sky roughly 49 times the area of the full moon, at depths sufficient to detect objects billions of times fainter than anything visible to the naked eye. The methodology of the Planet 9 search is deceptively simple in principle and enormously demanding in execution. A region of sky is photographed with precision. Weeks or months later, the identical region is photographed again. The two images are then compared, either by trained human eyes or, far more commonly now, by purpose-built algorithms designed to identify any point of light that has shifted position between the two exposures. Stars and galaxies fixed at their vast distances do not move on timescales of weeks. Planets, moons, asteroids, and comets do. Any object that appears in a measurably different position across two images taken at different times becomes a candidate requiring follow-up. This technique, called blink comparison, is the same fundamental method that led to Pluto's discovery in 1930, when astronomer Clyde Tombaugh spent months manually comparing photographic plates until a single point of light revealed itself by moving. For Planet 9, the process operates at a scale that Tombaugh couldn't have imagined. The search area spans hundreds of square degrees of sky. The image archive runs into the hundreds of thousands of individual frames. The algorithms processing those frames generate thousands of candidate objects per survey run, the overwhelming majority of which are quickly identified as known asteroids, background galaxies, or instrumental artifacts. For those that survive initial screening, additional observations on subsequent nights allow trajectory calculations and comparisons against comprehensive catalogues of known solar system objects. The process is meticulous, iterative, and in its daily reality almost entirely devoid of dramatic moments. What it has produced so far is something quieter but equally valuable, a systematic and expanding map of where Planet 9 is not. Large portions of the predicted orbital arc have now been imaged at depths sufficient to detect Planet 9 if it occupied those positions. It does not. The remaining search space contracts with every completed survey run, smaller than it was 12 months ago, smaller than it will be 12 months from now. Each image that returns without a discovery is not a failure. It is a constraint, a narrowing of the possible, a tightening of the geometry of the search. The researchers conducting this work describe their state of mind with a specific kind of patience that sits somewhere between scientific discipline and quiet certainty. Every image taken is either the one that ends the search with discovery, or the one that specifies more precisely where the discovery will eventually be made. In a search of this kind, both outcomes move the story forward, and the story, by every current measure, is moving steadily toward its conclusion. In the mountains of northern Chile, at an elevation of 2,662 meters above the Atacama Desert, one of the most consequential astronomical instruments in the history of planetary sciences is either already operational or approaching full survey capability. The Vera Rubin Observatory, named for the astronomer whose painstaking observational work provided the most compelling early evidence for the existence of dark matter. Known during its long construction phase as the Large Synoptic Survey Telescope, the Vera Rubin Observatory was designed from its earliest conceptual stages to accomplish something no telescope has ever done before: photograph the entire visible sky, repeatedly and systematically, in a continuous survey that accumulates over a decade into the most complete and dynamic map of the observable cosmos ever assembled. Its camera, formally designated the LESTI camera, and representing years of engineering collaboration across multiple institutions, contains 3.2 billion pixels, making it the largest digital camera ever constructed for an astronomical application. It captures a field of view 3.5 degrees across in a single exposure, equivalent to the area of roughly 7 full moons side by side. Every 3 nights, the observatory completes a full pass of the accessible sky, building a catalogue that will ultimately contain records for tens of billions of individual objects, and for each one of them, a continuous record of how its brightness and position change over time. Objects that move will be automatically flagged. Objects that vary in brightness will be catalogued. Objects that appear where nothing appeared before will trigger immediate alerts. For the Planet 9 search specifically, the Vera Rubin Observatory addresses, in a single instrument, both of the fundamental obstacles that have prevented discovery so far. The first obstacle has been sensitivity, the need for a telescope deep enough to detect something as faint as Planet 9 at its predicted distance. The Vera Rubin Observatory detects objects approximately 100 times fainter than any previous wide-field survey telescope, placing Planet 9 firmly within its detection range if the current orbital predictions are even approximately correct. The second obstacle has been coverage, the need to search not a targeted patch of sky, but the entire predicted arc, without assuming in advance which portion of that arc the planet currently occupies. The Vera Rubin Observatory covers the entire accessible sky every 3 nights, by design, without requiring anyone to choose which region deserves the next look. The combination of those two properties, extraordinary sensitivity paired with complete sky coverage, is what no previous instrument has achieved. Individual powerful telescopes like Subaru's Hyper-Suprime are capable of the required depth, but their coverage is deliberate and targeted. Wide-field survey telescopes from earlier generations cover the sky more broadly, but lack the sensitivity to detect something as faint as Planet 9 at its predicted distance. The Vera Rubin Observatory was built, in a design sense that feels almost purposeful in retrospect, to close precisely that gap. Complementing it from above the atmosphere is the Nancy Grace Roman Space Telescope, a NASA wide-field observatory named for the agency's first chief of astronomy, whose advocacy for space-based science shaped generations of missions. Operating in the infrared from a position beyond Earth's atmospheric interference, the Roman telescope carries a camera with a field of view 100 times larger than Hubble's while maintaining comparable image sharpness. For detecting a cold object like Planet 9, which radiates significantly more energy in the infrared than it reflects in visible light, the Roman telescope's wavelength sensitivity represents a particularly well-matched tool. 2 observatories, 2 different physical environments, 2 independent detection methodologies, both converging over the coming years on the same shrinking region of sky. The probability of Planet 9 remaining undetected past the end of this decade, if it occupies the parameter space currently predicted, is declining towards something that stops feeling like a probability and starts feeling like a timeline. The question is no longer whether the instruments are capable of finding it. The question is whether the institutions operating those instruments will present what they find with the transparencies that a discovery of this magnitude demands, or whether the pattern of careful, managed communication that has characterized the last decade of Planet 9 coverage will continue into the moment of confirmation itself. That question has no comfortable answer yet, but the technology, at least, is no longer on the side of concealment. The most honest form of inquiry is the one that turns its methods on itself, that asks not only whether the evidence supports the hypothesis, but whether the evidence might support something else entirely. The Planet 9 hypothesis has attracted serious scientific challenge since the day it was published, and the strongest of those challenges deserve to be presented plainly, without the kind of selective presentation that advocacy sometimes produces. Because the alternative to Planet 9, if the orbital clustering of trans-Neptunian objects is real and not an artifact of observational bias, is not simply nothing is out there. It is something potentially stranger. The most technically rigorous challenge to the Planet 9 hypothesis came from a 2019 study by researchers Antranik Sefilian and Jihad Tuma. Their paper proposed that the orbital clustering observed among the extreme trans-Neptunian objects, the feature that Batygin and Brown identified as a gravitational fingerprint of a massive, unseen planet, could instead be produced by the collective gravitational influence of a distributed disk of smaller objects in the outer solar system. Not one large planet, but a broad ring or disk of ice, rock and debris, each individual piece far too small to detect directly, but collectively massive enough to generate the same kind of gravitational shepherding effect that the Planet 9 hypothesis assigns to a single body. The disk model is mathematically coherent. It has not been refuted. It remains a legitimate alternative in the current scientific literature. Batygin and Brown engaged with this challenge directly in subsequent papers, pointing to specific features of the observed orbital clustering, particularly the anti-alignment of the orbital poles of the most extreme objects, that the disk model reproduces less naturally than a single massive perturber. Their arguments are technically detailed and persuasive to many researchers in the field, but they are arguments, not proofs, and the distinction matters. The disk model remains standing. The observational bias argument presents a different kind of challenge, one that is conceptual rather than competitive. The trans-Neptunian objects, whose clustering forms the basis of the Planet 9 hypothesis, were discovered over decades by telescopes that, for entirely practical historical reasons, surveyed certain regions of the sky far more thoroughly than others. If the survey coverage is significantly non-uniform, and it is, then the apparent clustering of discovered objects might reflect not a gravitational influence, but simply the pattern of where astronomers chose to look. Objects found predominantly in well-surveyed regions will naturally appear to cluster in those regions, even in the absence of any physical cause. This argument was taken seriously enough that Batygin and Brown addressed it specifically in follow-up work, incorporating data from surveys with more uniform sky coverage and demonstrating that the clustering signal persists after corrections for known observational biases are applied. Their conclusion, that the clustering is real and not artifactual, is supported by subsequent independent analyses. But the observational bias argument has not been rendered completely moot, and it is regularly invoked by researchers who approach the hypothesis with skepticism. What these competing explanations collectively illuminate is something more interesting than a simple scientific disagreement. They reveal that the outer solar system, at the absolute frontier of our current detection capability, is genuinely and deeply not yet understood. Whether the unexplained orbital patterns reflect a single massive planet, a distributed debris structure, a statistical artifact of limited surveys, or something that current theoretical frameworks don't yet have adequate language to describe. All of these remain live possibilities. And live possibilities at the frontier of knowledge have a long and humbling history of resolving in ways that surprise every faction in the debate, including the one that turns out to be approximately correct. The outer solar system is not finished surprising us. What remains uncertain is only the precise nature of the next surprise, and how long the institutions responsible for finding it will take to share it. There is a particular category of scientific discovery that doesn't simply expand the map. It forces a redrawing of the entire map from the beginning. Not an addition to existing knowledge, but a structural revision of the framework within which existing knowledge was organized. The discovery of Planet 9 would belong to that category. Not because a 10th planet would be, in itself, an unprecedented kind of object, but because its existence at its predicted location, with its predicted mass, in its predicted orbit, cannot be accommodated within the current standard model of solar system formation, without requiring that model to be fundamentally reconsidered. The standard model, developed through decades of computational refinement, and substantially supported by the study of planetary systems around other stars, begins with a disk. a flat rotating disk of gas and dust surrounding the young sun, extending outward to distances of perhaps a few hundred astronomical units, gradually organizing itself through the process of accretion into the diverse population of objects that now orbit our star. Rocky planets form close in, where temperatures were too high for ices to survive. Giant planets form at intermediate distances, where conditions allowed the rapid accumulation of massive gas envelopes around solid cores. The outer edges of the disk become the reservoir of comets and small bodies. The architecture to make physical sense, and computational simulations of this process consistently produce solar systems that look broadly like ours. They do not produce a super-Earth at 500 astronomical units. A world of Planet 9's predicted mass at Planet 9's predicted distance falls so completely outside the parameter space of standard planetary formation that its existence would require either a radical modification of the formation model or the acceptance of a process. Planetary capture from another stellar system that current models treat as a rare exception rather than a common mechanism. Either conclusion carries implications that extend well beyond our own solar system. If Planet 9 formed here and was ejected, the early solar system was more dynamically violent than the standard model comfortably accommodates. Violent enough to throw a super-Earth to the outermost edge of the sun's gravitational reach without losing it entirely. If Planet 9 was captured from another star, then the process of planetary exchange between neighboring stars in early stellar nurseries was common enough to have affected multiple solar systems, meaning that other stars in our galactic neighborhood may contain worlds that originally formed around our sun. Neither of these revisions is minor. Both require looking at the formation and early history of our solar system with different eyes than the ones the standard model provides. The sun's axial tilt adds another dimension to the reckoning. Most people know that Earth is tilted on its rotational axis, an inclination responsible for Earth's seasons. Less commonly known is that the sun itself sits at approximately a 6-degree tilt relative to the mean orbital plane of the 8 known planets. This misalignment has puzzled planetary scientists for years. Standard formation theory predicts that a star and the disk that forms its planets should share the same rotational orientation. They arise from the same collapsing cloud of gas and dust, after all, and that collapse should impose a common angular momentum on both the central star and the material orbiting it. 6 degrees of tilt is small, but it is real, measurable, and unexplained. In 2016, Batygin and Brown proposed that the gravitational torque exerted by Planet 9, a massive body in a significantly inclined orbit, operating over billions of years, could produce exactly this kind of misalignment between the sun's rotation axis and the planetary orbital plane. The calculation aligned with the observed tilt. The prediction matched the data without requiring any additional free parameters. A world we have never seen may have been slowly, patiently, imperceptibly tilting our sun for 4 billion years. And we have been recording that tilt without understanding its cause for decades. Until now. The implications of Planet 9's existence do not stop at the architecture of the solar system. They extend through a chain of gravitational logic that is uncomfortable to follow to its conclusion, to the surface of the Earth itself, to the fossil record, to the history of life, and to the question of what has periodically and catastrophically reset the biological clock of our planet across deep time. Beyond the orbit of Neptune, at distances ranging from a few thousand to perhaps 100,000 astronomical units from the Sun, lies the Oort cloud, a vast, roughly spherical reservoir of icy bodies left over from the earliest period of the solar system's formation. The Oort cloud is one of the few major components of the solar system that has never been directly observed. Its existence is inferred from the behavior of long-period comets, objects that arrive in the inner solar system on trajectories consistent with having fallen inward from enormous distances, looping around the Sun, and returning to the outer darkness on orbital periods measured in thousands or millions of years. The cloud itself is thought to contain hundreds of billions of individual objects, possibly more. The frozen remnants of material that was never incorporated into planets, preserved in the cold and dark at the outermost boundary of the Sun's gravitational influence. Under ordinary conditions, Oort cloud objects are stable. Their orbits are distant and nearly circular, and without an external perturbation of meaningful magnitude, They remain exactly where they have been for billions of years. But if something disturbs them, if a gravitational influence of sufficient strength nudges a fraction of those bodies onto trajectories that send them falling inward toward the sun, the inner solar system experiences what planetary scientists call a comet shower, a wave of objects streaming inward over millions of years, crossing the orbital paths of the planets. Some of those objects, following the ruthless arithmetic of orbital mechanics, will intersect with Earth. This is not conjecture. The geological and fossil record of Earth contains multiple periods of dramatically elevated impact rates, several of which correlate with the mass extinction events that have punctuated and redirected the history of life on this planet. The most famous is the End Cretaceous extinction 66 million years ago, the event that ended the age of non-avian dinosaurs and cleared the ecological space that eventually allowed mammals, and eventually humans, to become the dominant complex life forms on Earth. Less famous but equally total was the End Permian extinction 252 million years ago, which eliminated approximately 96% of all marine species and 70% of terrestrial vertebrate species in what geologists call, with characteristic understatement, the Great Dying. The question of what triggers these periodic catastrophes has occupied paleontologists and astrophysicists in roughly equal measure. In the 1980s, researchers including David R. Raup and Jack Sepkoski identified what appeared to be a rough periodicity in the mass extinction record, a cycle of approximately 26 to 27 million years separating the major extinction events. If that cycle is real and not a statistical artifact, something must be driving it. Something with a timescale of tens of millions of years, a timescale that points naturally toward astronomical rather than geological causes. The Nemesis hypothesis, proposed in the same decade, suggested that the Sun has a distant, dim companion star, a red dwarf or brown dwarf in a long orbit, whose periodic close approach to the Oort cloud triggers comet showers on each pass. No such companion star has been found, and the WISE survey effectively ruled out the existence of a bright enough object within the relevant distance range. Planet 9 is a different mechanism, operating on a different timescale. Its orbital period of 10,000 to 20,000 years does not match the 26 million year extinction cycle directly. But the outer solar system is not a simple system, and the gravitational dynamics between a massive inclined planet, the Oort cloud, and the galactic tidal forces that also act on it can produce complex resonance cascades, chain reactions or orbital perturbation that propagate through the comet reservoir over millions of years. Whether Planet 9 sits somewhere in that chain of causation connecting the outer solar system to the mass extinction record is a question that current models cannot definitively answer. What they can say is that Planet 9, if it exists, is massive enough and orbital enough to matter. And the history of life on Earth has been shaped, more than once, by objects falling inward from the cold dark where Planet 9 is hiding. Every great expansion of the known universe has been, at its deepest level, a story about what it means to be human. Not just what we know, but who we are in relation to what we know. Each time the map has been extended, the extension has required a revision of the story humanity tells about its own position in the larger order of things. And each of those revisions, however humbling in the immediate moment, has ultimately produced not a diminished sense of human significance, but a larger and more honest one. The Copernican revolution removed Earth from the center of the universe and placed it as one planet among others orbiting a commonplace star. The discovery of other galaxies revealed that the Milky Way, the home of every human being who ever lived and every civilization ever built, is one of hundreds of billions of comparable structures, unremarkable in scale and position. The confirmation of exoplanets around other stars reframed the question of life's uniqueness from a philosophical abstraction into an empirical one, with billions of candidate worlds now identified as potentially habitable. Each step has been a recalibration, and yet humanity has absorbed each one and continued forward, building more powerful telescopes, asking harder questions, extending the map further into the dark. The recalibrations did not diminish the impulse that produced them. They deepened it. Discovering Planet 9 would be another such moment. A 10th planet, orbiting our own sun, massive and real and hiding in the dark, beyond the reach of everything we had previously pointed at the sky. That discovery would arrive not as a quiet academic footnote, but as a cultural event of the first order. A revision not just to the scientific textbooks, but to the intuitive model that billions of people carry in their minds of what the solar system is and how completely we understand it. The scientific community would celebrate in the specific, restrained way that scientists celebrate. Papers published, press conferences convened, nomenclature committees convened by the International Astronomical Union to agree on what the new world should be called. But beneath that institutional response, something larger would be happening. A recognition, spreading through the culture at the speed of news and social media, and the million informal conversations that constitute the real processing of major events, that the neighborhood we thought we knew completely contained a room we had never entered. The more uncomfortable dimension of that recognition would arrive slightly later, as it always does. If Planet 9 has been mathematically predictable since 2016, and if its gravitational fingerprints have been detectable in trans-Neptunian orbital data for far longer than that, and if the Pioneer spacecraft were carrying evidence of its existence in their trajectory data for 50 years, then the question of why it took so long to confirm it becomes unavoidable. And the answer to that question requires looking not at the universe, but at the institutions we charged with exploring it. At the funding decisions, and the telescope allocation processes, and the press releases that translated technical papers into public narratives that were consistently less informative than the underlying science warranted. That accounting, honest, specific and overdue, would be one of the most important consequences of the discovery. Not because it would vindicate any particular conspiracy theory, and not because it would expose any individual as dishonest, but because it would demonstrate, in the most concrete possible terms, that the mechanisms by which scientific knowledge reaches the public are subject to pressures and distortions that the public has a right to understand. That knowledge is a social process before it is a public product, and that the next time an institution tells us the map is complete, we have been given abundant reason to ask what lies just beyond the edge they drew. There are moments in the history of science when a story appears, briefly illuminates something that seems important, and then disappears, not because it was proven false, but because it was never fully examined before the silence closed back over it. The story of what the IRAS satellite detected in 1983 is one of those moments. It lasted less than a month in public consciousness. It was explained away with a speed and completeness that, in retrospect, invites questions that were never asked loudly enough at the time. IRAS, the infrared astronomical satellite, was a joint mission of the United States, the United Kingdom and the Netherlands, launched in January of 1983. It was the first space-based observatory to survey the entire sky at infrared wavelengths, and it accomplished something genuinely remarkable. In less than a year of operation, it catalogued over 350,000 infrared sources, identified previously unknown galaxies, discovered new comets, and produced data that astronomers are still mining for discoveries today. It was, by any measure, one of the most productive astronomical missions ever flown. In December of 1983, the Washington Post published a story under a headline that even now stops the eye. A mysterious celestial body had been discovered in the direction of the constellation Orion. The IRAS scientists had detected it in multiple observations, and it was described as possibly being as large as Jupiter, and possibly close enough to be part of our own solar system. The scientist quoted in the story, JPL's Jerry Neugebauer, one of the principal IRAS investigators, reportedly described the object as defying easy explanation and warranting further study. The story ran. It was picked up by other outlets. For a brief period, it appeared that IRAS had found something genuinely significant in the outer solar system. Within weeks, the story was effectively closed. Scientists associated with the mission clarified that the mysterious object had been several different candidate sources in the data, most likely distant galaxies seen edge-on, which can produce infrared signatures that initially resemble compact nearby objects before longer baseline observations resolve them into their true nature. The explanation was technically plausible. The scientific community accepted it. The press moved on. The story was categorized as a misunderstanding, a communication error between scientists and journalists, and filed away. But examining what actually happened in that data, not the press coverage, which simplified at every step, but the original scientific communications between IRAS team members in the weeks surrounding the story, reveals a picture more textured than the official resolution suggested. The unidentified infrared sources that generated the initial excitement were not a single anomaly, but a cluster of detections that the team found genuinely difficult to classify in real time. The process of ruling them out as galaxies was not instantaneous. It required additional analysis and, in some cases, follow-up observations that took months. The speed with which the public story was closed did not fully reflect the speed at which the scientific analysis was actually completed. What the IRAS incident establishes, set against the broader pattern of Planet 9-related communication, is a precedent, a template for how potentially significant detections in the outer solar system tend to be handled publicly. The sequence is consistent: detection, initial excitement, rapid official explanation, public story closed, technical details available to specialists but effectively inaccessible to general audiences. Whether the IRAS sources were truly unexplained objects in the outer solar system or misidentified distant galaxies is a question the available evidence cannot definitively answer. What the incident does with certainty is demonstrate that the infrastructure for rapidly and authoritatively closing a public story about an outer solar system anomaly has been in place and operational since at least 1983, and that infrastructure has not been dismantled. It has, if anything, grown more sophisticated in the decades since. The question worth sitting with is not whether IRAS found Planet 9. The question is whether the institutional response to that detection, whatever it actually was shaped more by the evidence or by something else entirely. And that question connects directly to a mission launched 27 years later, whose results were presented to the public, with a similar combination of selective emphasis and carefully managed conclusion. In December of 2009, NASA launched the Wide Field Infrared Survey Explorer, WISE, on a mission specifically designed to survey the entire sky at 4 infrared wavelengths, with sensitivity and coverage far exceeding any previous space-based infrared observatory. WISE was, in the language of its mission documentation, designed to find what previous surveys had missed: cool, dim objects that emit most of their energy as heat rather than light, invisible to optical telescopes but detectable to a sufficiently sensitive infrared instrument pointed in the right direction. The mission was enormously successful by any scientific standard. WISE discovered hundreds of previously unknown near-Earth asteroids, identified thousands of new brown dwarf stars in the solar neighborhood, catalogued millions of distant galaxies, and produced an all-sky infrared atlas that astronomers continue to use as a foundational reference. When its primary mission was completed and its cryogenic coolant exhausted, the telescope was repurposed for an asteroid-hunting follow-up mission called NEOWISE. By every measure, WISE delivered on its scientific promise. In 2012, a paper by researchers using the WISE dataset published conclusions about the outer solar system that received significant and immediate press coverage. The paper established that no object with a mass comparable to Saturn or Jupiter existed within a certain distance from the Sun, approximately 10,000 astronomical units for a Jupiter mass object, and somewhat less for a Saturn mass one. Headlines appeared within days across the world's science and general media. Planet X ruled out. Nemesis star does not exist. The solar system has no hidden giant companions. The stories were confident, comprehensive, and globally distributed. The technical paper was more precise and considerably more limited. The WISE constraints applied specifically to warm, massive objects, bodies large enough and internally heated enough to radiate significant infrared energy at the wavelengths WISE was optimized to detect. For a cold super-Earth or mini-Neptune, an object of the type and mass that the Planet 9 hypothesis describes, at the distances Planet 9 is theorized to occupy, the WISE survey's sensitivity was substantially reduced. The specific detection threshold for cold, small objects at 500 to 800 astronomical units was stated in the paper's methodology section with careful accuracy. It did not rule out Planet 9. The instrument wasn't designed with that specific detection in mind, and the survey depth at the relevant temperatures and distances was insufficient to produce a definitive constraint. That qualification appeared in the technical paper. It did not appear in the press releases. It did not appear in the headlines. The gap between what WISE actually demonstrated and what the public was told it demonstrated was not a minor technical nuance. It was a categorical difference between "we did not detect warm giant planets within this distance range" and "there are no undiscovered planets in our solar system." Those two statements are separated by an enormous amount of scientific space. The translation from one to the other, in every mainstream media outlet covering the story, happened without apparent awareness of the distinction. A 2014 reanalysis of the WISE data, conducted specifically to assess its sensitivity to Planet 9 type objects, identified several uncharacterized infrared point sources at positions consistent with distant solar system objects. These sources were flagged in the reanalysis paper as warranting follow-up observation. The follow-up, if it was conducted through official channels, has not produced any publicly documented report. The sources remain uncharacterized in the published literature. Whether they were subsequently ruled out through unpublished analysis, or remain genuinely unresolved, is not a question the available public record can answer. What the WISE episode adds to the cumulative picture is a specific and documented example of a gap between institutional scientific communication and the actual content of the underlying research. That gap may be the result of ordinary science journalism failures, the kind of simplification that occurs whenever complex technical results are translated for general audiences by people who lack the specialist background to preserve the important qualifications. Or it may reflect something more deliberate. The distinction between those two explanations matters enormously, and the pattern in which this gap consistently appears and consistently closes stories rather than opening them makes the more comfortable explanation progressively harder to sustain. To understand how knowledge about the outer solar system is produced, managed, and presented to the public, it helps to understand who pays for the telescopes, who decides what gets published, and who controls the language in which discoveries are described when they travel from specialist journals to the awareness of general audiences. Because astronomy, for all its association with pure and disinterested inquiry, is embedded in funding structures, institutional hierarchies, and political relationships that shape its outputs in ways that are rarely discussed openly and almost never appear in the press releases accompanying major discoveries. The overwhelming majority of large-scale astronomical research in the United States is funded either directly by NASA or through the National Science Foundation, which administers competitive grant programs that determine which research directions receive resources and which do not. Both agencies answer ultimately to congressional appropriations, meaning that the direction of American astronomy is, at its funding root, a political question as much as a scientific one. Priorities are set not purely by scientific merit, but by a complex negotiation between scientific community recommendations, agencies' strategic plans, congressional interests, and the broader geopolitical context in which space exploration operates. Researchers who work within this system understand, without needing it explained, that certain lines of inquiry are more fundable than others, and that the unfundable ones tend to be the ones that produce the most friction with established institutional narratives. The peer review system that governs what gets published in major astronomical journals is operated by the same community of scientists who hold the tenured positions, control the telescope allocation committees, and sit on the grant review panels. This is not a conspiracy. It is the ordinary documented operation of a professional scientific community organized around expertise and reputation. But it creates a structural condition in which the same individuals who stand to be most professionally disrupted by a major revision of the solar system's architecture are the ones making decisions about whether research supporting that revision receives the resources and publication venues needed to develop into a confirmed discovery. That structural condition does not require anyone to act in bad faith. It produces its effects through the entirely ordinary human tendency to apply higher skepticism to claims that threaten established positions than to claims that support them. The International Astronomical Union, the body that officially classifies and names astronomical objects and whose 2006 vote demoted Pluto from planetary status, operates through voluntary compliance by its member nations. Its authority over what constitutes a planet, what an object is named, and how discoveries are officially described is real within the scientific community, but has no enforcement mechanism beyond professional consensus. In a world where privately funded observatories are growing in number and capability, and where the first confirmation of Planet 9 might arrive not through a government-funded telescope, but through an instrument operated by a private foundation or commercial entity, the IAU's ability to manage the narrative around that discovery is significantly less than it would have been a generation ago. Private funders, the Breakthrough Initiatives Program, backed by Yuri Milner, the various philanthropic science foundations that have funded independent telescope projects, and the commercial space companies developing deep space observation capabilities, operate under no obligation to publish findings in open access journals, to notify government agencies before announcing results, or to frame their discoveries in the careful, qualifying language of institutional science communication. If a privately funded telescope detects Planet 9, the decision about when to announce the discovery, how to describe it, and who to tell first belongs entirely to whoever controls the funding. That is a fundamentally different disclosure architecture than the one that governed every previous major planetary discovery in history. The sky, in other words, is no longer controlled by a single set of institutions with a single set of incentives around transparency. It is being watched by an expanding, diverse, and partially competing set of actors whose interests do not all point in the same direction. And somewhere in the space between their competing interests, the answer to the Planet 9 question is waiting, already encoded in light that has already travelled billions of kilometres to reach a telescope that has already recorded it, or will soon. In every field of human knowledge, there exists a category of claim that occupies an uncomfortable middle position, too serious to dismiss outright, too disruptive to embrace without extraordinary evidence, and too persistent to disappear simply because the institutions responsible for evaluating it have chosen not to engage with it directly. These claims tend to be made by individuals rather than institutions, to appear at the edges of mainstream discourse rather than at its centre, and to attract a mixture of genuine, intellectual curiosity and reflexive ridicule that makes dispassionate evaluation unusually difficult. The history of outer solar system research contains several such claims, made by individuals with genuine scientific credentials that have received far less serious engagement than their technical basis would seem to warrant. Robert Sutton Harrington was an astronomer at the United States Naval Observatory, one of the most prestigious astronomical institutions in the country, who spent the final years of his career conducting a dedicated search for a massive undiscovered body in the outer solar system. Working in the late 1980s and early 1990s, Harrington developed a mathematical model predicting the location of what he called Planet X, an object whose gravitational influence he believed was detectable in the orbital perturbations of Neptune and Uranus. His calculations placed the object in the southern sky at a distance and declination that differed from the current Planet 9 predictions, but reflected the same fundamental methodology, using orbital anomalies to infer the position of an unseen perturber. Harrington's search was real, documented, and conducted with professional rigour. He used naval observatory facilities to conduct a systematic photographic survey of the southern sky in the region his calculations identified. He corresponded with colleagues about his findings, presented his work at professional conferences, and published papers describing his methodology and results. He died in January of 1993 at the age of 50, before his search was complete. His research program was not continued by anyone at the Naval Observatory after his death. The photographic plates from his survey were archived. The mathematical work he had developed over years was not built upon by subsequent researchers at the institution where he had spent his career. His name almost never appears in mainstream discussions of the Planet 9 hypothesis. When it does appear, it is typically in a footnote, acknowledged briefly as an early predecessor, and then set aside. The accumulated research of a Naval Observatory astronomer who dedicated the last decade of his professional life to finding exactly what Batygin and Brown later claimed to have mathematically predicted. That research has not been absorbed into the current search program, has not been cited as foundational, and has not been examined for what it might have found or narrowly missed. The Paton-Harrington story represents a credentialed researcher pursuing an uncomfortable hypothesis, dying before completion, and being subsequently not quite forgotten but not quite remembered, is not unique to him. It appears with variations across several decades of outer solar system research. The researchers involved were not cranks. They were not producing fabricated data or making claims beyond what their evidence supported. They were following the same gravitational logic that eventually led to Batygin and Brown's celebrated 2016 paper, using instruments and datasets available to them at their respective moments in the history of the field. What they lacked was not rigor but institutional momentum, the specific combination of prestigious affiliation, timely publication, and media engagement that transforms a scientific hypothesis from an archived curiosity into a globally covered story. The difference between a suppressed discovery and a simply overlooked one is, in practice, very difficult to establish. What can be established is the pattern, and the pattern in outer solar system research is consistent enough, across enough researchers and enough decades, to warrant something more than a shrug. Beyond the journals and the observatories and the conference rooms where professional astronomers debate the orbital mechanics of trans-Neptunian objects, there exists an entirely parallel conversation about Planet 9, Planet X, Nibiru, and the hidden bodies of the outer solar system. One conducted on YouTube channels, Reddit forums, dedicated websites, and the comment sections of science news articles by an audience numbering in the millions. This conversation is louder, faster, more emotionally engaged, and far less epistemically disciplined than the one happening in peer-reviewed literature. It is also, in ways that matter more than the scientific establishment is comfortable acknowledging, a direct product of the institutional communication failures that the previous chapters have described. The online Planet X community is not a monolith. At one end of its spectrum sit genuine enthusiasts, people without professional astronomical training but with real intellectual curiosity, who follow the published literature, track new TNO discoveries, read Batygin and Brown's papers, and ask questions about orbital mechanics that are sometimes more pointed than the questions appearing in mainstream science coverage. These communities have, on multiple occasions, identified significant developments in the Planet 9 story before they were covered by major science journalists, because the people in those communities were watching the Arxiv preprint server and the minor planet circulars while the press was waiting for an official announcement. At the other end of the spectrum sit the catastrophists, communities organized around the conviction that a rogue planet is on an imminent collision course with Earth, that its approach is being actively concealed by world governments, and that the evidence for this concealment is visible in everything from unusual weather patterns to the positions of chemtrails to the alleged existence of underground bunkers being constructed for elite survivors. These communities have predicted the Earth's destruction by inbound planetary body on specific verifiable dates in 2003, 2012, 2017, and several times since. Each prediction has failed. Each failure has been explained within the community by a revision of the timeline rather than a revision of the fundamental belief. The structure of unfalsifiability that these communities have built around their central claim is a classic example of what happens when genuine curiosity about an unanswered question is captured by a framework that has no mechanism for being wrong. The important question is not which of these communities is correct. The important question is why both of them exist at all, and why the audience for Planet X content online numbers in the tens of millions rather than the tens of thousands. The answer to that question is not that people are credulous or irrational. The answer is that a significant portion of the global population has, through entirely reasonable observation of the pattern described in these chapters, arrived at the conclusion that official sources cannot be trusted to tell them everything significant that is known about the outer solar system. That conclusion may be imprecise in its details and wildly wrong in its most extreme expressions, but its underlying premise, that institutional science communication around the Planet 9 question has not been fully transparent is, as this story has repeatedly demonstrated, not without foundation. The antidote to the rabbit holes is not more dismissal. It is not scientists sighing at the irrationality of the internet. It is the kind of radical, proactive transparency that the Planet 9 question has never received from the institutions responsible for answering it. The kind that addresses not just the technical evidence, but the communication failures that have allowed the space between what is known and what has been shared to become so wide that millions of people have filled it with their own unchecked narratives. Beneath the noise of the online conversation, and above the careful institutional hedging of official communications, there is a middle register that rarely receives the attention it deserves. The growing body of credentialed, publishing, institutionally affiliated astronomers who have gone on record, in peer-reviewed literature and at professional conferences, stating that the evidence for Planet 9 is strong, that the search deserves more resources than it is currently receiving, and that the scientific community's collective posture toward the hypothesis has been more conservative than the evidence warrants. Beyond Batygin and Brown themselves, the list of researchers who have contributed independent supporting evidence to the Planet 9 case is substantial. Scott Shepard of the Carnegie Institution for Science and Chad Trujillo of Northern Arizona University co-discovered several of the extreme trans-Neptunian objects whose orbital clustering forms the core of the evidential case. Their independent analyses of those objects' orbital properties have consistently supported the hypothesis that a massive distant perturber is responsible for the clustering. David Tholen of the University of Hawaii has contributed additional TNO discoveries and orbital refinements. Teams in Japan, Chile, and South Korea have added their own observations to the growing dataset. The hypothesis, far from being the pet theory of two Caltech astronomers, has developed into a research program involving dozens of investigators across multiple continents. In 2021, a paper published in the Astronomical Journal provided what was at that time the most precise constraint on Planet 9's predicted location and orbital parameters, synthesizing all available observational evidence into a refined model that narrowed the search area significantly. The paper was not a confirmation, but it represented the kind of systematic, multi-datasets convergence that in other areas of astronomy would be treated as the penultimate step before direct detection. The community producing this work was not a fringe. It was a cross-institutional, international research program applying standard astronomical methodology to a hypothesis that the available evidence had consistently declined to refute. What this community shares, beyond the technical work, is a specific kind of professional frustration that rarely surfaces in published papers, but appears in conference discussions and private communications. The frustration of researchers who believe they are following the evidence carefully and rigorously toward an important conclusion, and who find that the institutional infrastructure surrounding that conclusion remains systematically reluctant to commit the resources that would settle the question definitively. The Vera Rubin Observatory and the Roman Space Telescope represent the arrival of those resources. Finally, through instruments whose survey programs were designed with goals broader than the Planet 9 search, but whose capabilities are more than adequate for it. The community that has spent a decade narrowing the search space through targeted observations is now waiting for the survey era to deliver the confirmation that the targeted era has been building toward. That confirmation, when it arrives, will not be a surprise to the researchers who have been working toward it. It will be, in the specific emotional register of scientists who have spent years being asked to justify the importance of what they are looking for, something closer to vindication, the moment when the evidence that was always there, always compelling, and always just beyond the reach of the available instruments, finally resolves into something that no official communication can describe in its least informative form. A point of light in a photograph, moving against a fixed background of stars, in exactly the region of sky that the mathematics pointed to for years. Small, faint, real, and patient enough to have waited, in the dark beyond the edge of the known solar system, for exactly as long as it took us to build an instrument capable of seeing it. There is a version of the story of space exploration that presents itself as purely scientific, a collaborative, borderless pursuit of knowledge conducted by researchers who share data freely across national boundaries and celebrate each other's discoveries without regard for which flag flies over the institution that made them. That version is not entirely false. Genuine scientific collaboration across national lines is real and valuable and happens every day in astronomy, physics, and planetary science. But it coexists with another version of the same story, one in which the sky is a domain of competition, discovery is a form of national power, and the question of who finds something first carries implications that extend far beyond the academic. The space race of the 20th century established the template. The first satellite, the first human in orbit, the first moon landing. Each of these milestones was simultaneously a scientific achievement and a geopolitical statement, a demonstration of technological capability and national will directed as much at adversaries and allies as at the cosmos itself. The Cold War ended, the template did not. The 21st century has seen a new era of space competition develop between the United States, China, and the European space programs. One less openly militarized than the original space race, but no less consequential in its stakes. China's astronomical infrastructure has expanded dramatically over the past 2 decades. The 500-meter aperture spherical telescope, FAST, completed in 2016 in Guizhou province, is the largest single-dish radio telescope ever built, with sensitivity that surpasses any comparable instrument in the world. China's space agency has successfully landed rovers on the Moon and Mars, returned lunar samples to Earth, and outlined plans for deep space exploration that position the country as a genuine peer competitor to NASA in every domain of space science that carries strategic significance. Chinese astronomical programs are also increasingly capable in the optical and infrared survey domains most relevant to outer solar system research. If China were to confirm the existence of Planet 9 before an American institution does, the symbolic and political implications would extend well beyond astronomy. The discovery would be presented by Chinese state media, by the country's scientific establishment, and by the global audience processing the news, as evidence that the center of scientific gravity has shifted, that the instruments, the funding, the talent, and the institutional will required to make the most significant planetary discovery in a century now reside, or at least also reside, in a country that did not lead the space age. That framing would be difficult for American institutions to counter, and the awareness of that difficulty is not absent from the minds of the people who make decisions about telescope priorities and research funding in Washington. The discovery of Planet 9, in other words, is not a race only in the scientific sense. It is a race in the same sense that every major space milestone since 1957 has been a race. One where the prize is not only knowledge, but the narrative authority that comes with being the one who found what no one else had found. And narrative authority, in the geopolitics of the 21st century, is a form of power that no major nation is indifferent to. The telescopes are pointing, the algorithms are running, the search space is narrowing. And somewhere in the offices, where strategic decisions about space program priorities are made, the question of who gets to announce the discovery of the solar system's 10th planet has almost certainly been considered. The landscape of who controls major astronomical instruments has changed in ways that would have been almost unimaginable a generation ago. For most of the history of modern astronomy, the infrastructure for significant discovery was owned and operated by governments and universities, institutions with at least a nominal commitment to public disclosure of findings, operating under frameworks that treated scientific knowledge as a public good even when the instruments producing it were expensive and access to them was tightly managed. That framework shaped not only how discoveries were made, but how they were announced, credited, and communicated to the world. The entry of private capital into astronomy at scale has altered those assumptions in ways the field has not yet fully reckoned with. The Breakthrough Listen and Breakthrough Watch programs, funded by the Russian-Israeli technology investor Yuri Milner, through the Breakthrough Initiatives Foundation, have provided hundreds of millions of dollars to astronomical research programs, including projects relevant to outer solar system characterization, with a disclosure philosophy that is, in practice, more open than many government programs but subject, ultimately to the preferences of a private funder rather than the norms of a public institution. The Vera Rubin Observatory, though primarily government-funded, includes private philanthropic contributions that have shaped aspects of its data access policy. New private space companies are developing telescope platforms and satellite constellations that include Earth observation and astronomical capabilities, whose scientific outputs will belong, in legal terms, to their corporate operators. The International Astronomical Union's authority in this new landscape is more limited than it appears. The IAU classifies planets, assigns names, and maintains the official catalogue of solar system objects. But it exercises that authority through voluntary professional compliance by member institutions, not through any legal or regulatory mechanism. A private company that discovers Planet 9 and chooses to announce it under a proprietary name before filing the relevant discovery report with the Minor Planet Center faces no legal consequence for doing so. It might face professional criticism from the astronomical community. It might find that its chosen name fails to achieve official IAU recognition. But the discovery itself, the confirmed detection of a new massive body in the solar system, would be real regardless of how it was announced or by whom. The possibility of a private Planet 9 discovery is not as remote as it might seem. Several private observatories and funded survey programs currently operate instruments with at least partial sensitivity in the relevant parameter space. The data pipeline from raw observation to confirmed detection can, in principle, be compressed to weeks or months for a well-resourced private program focused specifically on the task. And if such a program found what it was looking for, the decisions around timing, framing, and disclosure would belong entirely to a small group of people in a room somewhere. Without the peer review processes, institutional consultations, and public affairs management that would govern the same announcement coming from NASA or the European Space Agency. This is not a theoretical concern. It is the actual current state of the astronomical discovery landscape. And it means that the story of Planet 9's eventual confirmation may not follow the pattern of previous planetary discoveries. The careful paper, the press conference, the IAU committee, the textbook revision. It may arrive as a press release from a private foundation, or a social media post from a technology billionaire's personal science project, or an announcement at a commercial space conference before it appears in any peer-reviewed journal. The mechanisms for that kind of announcement have no historical precedent in the context of a discovery this significant. And the institutional astronomy community, which has spent a decade carefully managing the narrative around Planet 9, may find itself watching the story escape the management structures it built for it. It would be satisfying and dramatically cleaner if the story of institutional silence around Planet 9 resolved into a simple choice between honesty and concealment. If the pattern of carefully managed communications could be attributed to a single decision made by a small number of people who knew the full truth and chose to withhold it, that version of the story would be emotionally coherent and narratively satisfying. It would also be almost certainly wrong. The reality of how scientific institutions handle discoveries at the frontier of knowledge is considerably more complicated, and that complexity deserves to be engaged with honestly, even in a story that has found genuine reasons to question the transparency of those institutions. Because the same institutions that have managed the Planet 9 narrative with frustrating care have also, in other contexts, demonstrated exactly the kind of careful, deliberate disclosure management that looks, from the outside, like suppression, but is driven from the inside by something more recognizable and in some cases more defensible than the desire to hide the truth. When LIGO confirmed the detection of gravitational waves in September of 2015, the team did not immediately announce it. They spent 4 months verifying the signal, testing every possible alternative explanation, running independent analyses, and preparing the communication strategy for an announcement that they knew would be one of the most significant in the history of physics. They were correct to do all of those things. The announcement, when it came in February of 2016, was precise, well-supported, and essentially unimpeachable. The 4-month gap between confirmation and announcement was not deception. It was responsibility. The question the Planet 9 situation poses is where the line between responsible verification and strategic delay actually sits, and who gets to draw it. A discovery supported by statistical evidence at the level currently available for Planet 9 has not been confirmed in the LIGO sense. Direct detection has not occurred. The careful institutional language describing it as a hypothesis rather than a confirmed finding is, in strict technical terms, accurate. But the gap between technically accurate and fully informative is where the real tension lives. An institution that describes the Planet 9 evidence as a statistical hypothesis without communicating that the statistics in question represent a less than 1 in 10,000 probability of coincidence is telling the truth in the narrowest possible sense while producing a significantly distorted picture in the mind of any non-specialist audience. That gap, maintained consistently over years across multiple institutions in the face of accumulating evidence, is the institutional behavior that this story has documented. It is not lying. It may not even be consciously coordinated. It may emerge simply from the natural tendency of cautious, credential-conscious, peer-review-embedded researchers to apply the most conservative possible framing to claims that carry professional risk. But its effect on public understanding is indistinguishable from the effect of a deliberate policy of soft suppression. And the people experiencing that effect, the curious, engaged, intelligent audience members who have followed this story and found the official communications consistently less informative than the underlying evidence, are not wrong to notice it. The truth about Planet 9, when it arrives in the form of a direct detection, will be complicated to disclose not because the discovery itself is complicated, but because the decade of communication choices that preceded it will require a reckoning. A reckoning not with a conspiracy, but with the ordinary, documented, entirely human tendency of institutions to protect their narratives, even when the evidence has quietly outgrown them. Strip away every layer of institutional politics, every question of suppressed data, every ancient text and anomalous spacecraft trajectory, and what remains at the center of the Planet 9 story is something clean and, in its way, beautiful. A convergence of independent mathematical arguments, each developed by different researchers using different datasets and different methods, all arriving at the same answer. 5 separate lines of evidence, 5 independent research programs, 5 different ways of listening to the solar system's gravitational whisper, and all 5 pointing, with varying degrees of precision, but with remarkable consistency of direction, to the same region of sky and the same approximate range of mass. The first line is the one that started everything. The orbital clustering of the extreme trans-Neptunian objects. The distant, small bodies beyond Neptune, whose orbital paths align in a way that the known solar system cannot explain. The probability of that alignment being random, calculated across multiple independent analyses, using different statistical methods, consistently falls below 1% and in the most rigorous treatments falls below 0.02%. This is not a marginal statistical signal. It is, in the language of particle physics, where the standard for claiming a discovery requires a 5 sigma confidence level, a result that would be taken as strong evidence of something real. The second line is the existence of highly inclined and even retrograde trans-Neptunian objects, bodies whose orbits are so severely tilted relative to the solar system's plane that no known mechanism in the standard model of solar system dynamics can account for them. Planet 9's gravitational influence, in the computational models developed by Batygin and collaborators, naturally produces exactly these kinds of highly inclined orbits through a process of secular resonance. Without Planet 9, these objects have no explanation. With it, they are a predicted outcome. The third line is the anti-alignment of the orbital poles of the most extreme known TNOs, a feature of their orbital geometry that is not only statistically improbable in the absence of a perturber, but is specifically predicted by the Planet 9 hypothesis in terms of its direction and magnitude. This is not a post hoc fit to the data. It is a forward prediction that the data subsequently confirmed. The fourth line is the solar obliquity, the 6-degree tilt of the Sun's rotational axis relative to the planetary orbital plane, which the Planet 9 hypothesis explains through long-term gravitational torque in a way that no previous solar system model had been able to account for, and which matches the observed tilt without requiring any additional free parameters in the model. The fifth line, less discussed but not less significant, comes from the orbital structure of the scattered disk. The population of objects in highly elliptical orbits that connect the classical Kuiper belt to the more distant trans-Neptunian space. The specific distribution of scattered disk objects shows structural features that computational models, including Planet 9, reproduce more naturally than models without it. 5 lines, 5 independent datasets, 5 separate research programs, no single line is proof. But the convergence of all 5 on the same physical object, at the same approximate distance, in the same approximate region of sky, produces a cumulative evidential weight that distinguishes the Planet 9 hypothesis from the class of interesting but inconclusive astronomical proposals and places it in a different category entirely, the category of things that the mathematics has already found. And that observation is simply catching up to. Gravity does not lie. It does not misremember. It does not produce 5 independent, consistent, quantitatively specific false signals pointing at the same empty region of sky. Something is there. The only honest remaining question is how much longer the telescope will take to confirm what the mathematics has been saying for a decade. Somewhere, right now, in the vast and continuously growing archive of astronomical images accumulated by the telescopes currently scanning the outer sky, there may already be a photograph that contains Planet 9, not identified, not flagged, not yet recognized for what it is, a faint, cold, slow-moving point of light in a field crowded with background stars, indistinguishable at a glance from the thousands of other faint points surrounding it. A world 10 times the mass of Earth, patient in its darkness, already captured in pixels on a detector, waiting for the comparison image that will reveal its motion and the analyst, human or algorithmic, who will recognize what that motion means. This is not a dramatic speculation. It is the statistical reality of how major solar system discoveries have historically worked. Pluto was photographed multiple times before Clyde Tombaugh's blink comparison identified it. Neptune existed in several earlier telescope images before its recognition, including, famously, in drawings made by Galileo, who observed it twice in 1612, but recorded it as a fixed star because he had no reason to expect a planet in that part of the sky. The answer in both cases was already in hand. Recognition lagged behind detection because the recognition required a framework the observer didn't yet possess. When Planet 9 is finally confirmed, the moment of actual discovery will most likely be quiet. A researcher, possibly a graduate student running automated comparisons of survey images, possibly a senior astronomer reviewing a candidate object list generated by the Vera Rubin Observatory's alert system, will notice a point of light that has moved between 2 images separated by days or weeks. The movement will be small, consistent with an object at several hundred astronomical units, moving at the orbital velocity predicted for Planet 9. Initial calculations will produce a preliminary orbit. The orbit will be wrong in its details. Early orbital solutions always are, before additional observations refine them. But it will be obviously, unmistakably consistent with a distant solar system body in a highly elongated, inclined orbit at the predicted distance. What happens next is both procedurally defined and emotionally uncharted territory. The researchers involved will immediately begin verification. Additional observations over subsequent nights to confirm the object's existence and refine its trajectory, comparisons against archive images from previous surveys to identify earlier appearances of the same object that were not recognized at the time, independent confirmation from a second observatory to rule out instrumental artifacts. This process will take days to weeks, not months. The evidence base for Planet 9's existence is already so well developed that the additional mathematical confirmation required to convert a candidate detection into a confirmed discovery will be achievable relatively quickly. The announcement, when it comes, will travel through the global information architecture at a speed that no previous planetary discovery has experienced. Within hours of an official confirmation, the story will be everywhere. Science outlets, general news, social media, the informal networks of curious people who have been following the Planet 9 search for years. The reaction will be enormous, layered, and genuinely complex. The astronomical community will celebrate in the measured, precise way that scientists celebrate landmark confirmations, with papers, with colloquia, with the particular satisfaction of people who spent years being asked to justify what they were looking for. The broader public will experience something rarer, the specific kind of wonder that comes from learning that the world is larger and stranger than the most authoritative sources had been prepared to tell you. And beneath both reactions, a quieter reckoning will begin. The decade of careful institutional communications about Planet 9. The press releases that described statistical evidence in its most conservative framing. The headlines that translated bounded survey results into sweeping negative conclusions. The researchers whose work was quietly set aside. The data from missions decades old that pointed towards something no one in authority was prepared to confirm. All of that history will be available for examination. In an era when the thing it's sounded has finally been confirmed to be exactly what the evidence always suggested it was. That examination will not be comfortable for the institutions involved. It should not be. Discomfort in this case is the appropriate response to a decade of telling people less than the evidence warranted. Every map ever drawn by human hands has had an edge. Not because the world ended there, but because human knowledge ended there. Because the ships had not yet sailed far enough, the instruments had not yet been built sensitive enough, the mathematics had not yet been developed precise enough to describe what lay beyond. At those edges, medieval cartographers wrote phrases that have become famous precisely because of what they reveal about the human experience of the unknown. Here be dragons. Not a literal belief, in most cases, that monsters inhabited the uncharted territories, but an honest acknowledgement that beyond the boundary of the known, the familiar categories stopped working. That the rules might be different. That what waited in the unmapped space might not resemble anything the map had prepared you for. We are standing at one of those edges right now. The solar system we have described for the past several decades. 8 planets, a belt of asteroids, a scattering of dwarf worlds, a distant cloud of comets, is a map drawn to the boundaries of what our instruments could confirm at the time they were calibrated. It is accurate within those boundaries. It is not complete. And the evidence accumulated over the past decade suggests, with a statistical confidence that leaves almost no room for comfortable dismissal, that just beyond the current boundary of our confirmed knowledge, something enormous has been waiting with the patience of a world that measures its years in 10 millennia. What the search for Planet 9 has already revealed, regardless of whether a direct detection has yet occurred, is a set of truths about the way human institutions handle knowledge at the frontier that are at least as important as any astronomical discovery. It has revealed that the mathematical tools we possess are powerful enough to infer the existence of objects our optical tools cannot yet reach, and that this gap between inferential knowledge and confirmable proof is a space in which institutional behavior is not always guided purely by the pursuit of truth. It has revealed that the history of astronomical discovery contains researchers and research programs that were not given the resources and recognition their work deserved, and that the distribution of those resources and that recognition follows patterns that have more to do with institutional hierarchy than with scientific merit. It has revealed that the public communication of frontier science is shaped by forces, funding pressures, career incentives, narrative management, and the natural conservatism of communities with large investments in existing models that consistently produce a more cautious and less informative public record than the underlying evidence supports. These are not comfortable revelations, but they are important ones, because the response to them is not cynicism, not the conclusion that science is simply another form of institutional power, and that its claims to special authority over questions of fact are therefore no more trustworthy than any other institution's claims. That conclusion mistakes the map for the territory. Science, for all its human imperfections, remains the most reliable method humanity has developed for distinguishing what is true from what is merely believed. Its results, accumulated over centuries and tested against reality in ways that no other form of inquiry can match, are the foundation on which every technology, every medicine, every communication system you are using right now was built. The lesson of the Planet 9 story is not that science is broken, it is that science is human. And human systems require not blind trust, but informed, engaged, persistent attention from the people they serve. The watchers need watching. The mapmate to know that the people reading their maps are paying close enough attention to notice when the edge has been drawn too soon. There is a planet at the edge of our solar system. The mathematics says so. The evidence says so. The pattern of what has been said and left unsaid by the institutions responsible for confirming it says so in its own way. It has been there for billions of years, moving in its vast, tilted, patient arc through a darkness that our sun barely reaches. It has watched, in the only sense that a world can watch, as the small, warm, brief civilizations on the third planet, from that sun gradually develop the instruments and the courage to look outward far enough to find it. The instruments are ready. The courage is the part that remains to be confirmed. And when both finally align, when a telescope goes to the right patch of sky on the right night, and a point of light moves against the stars, the edge of the map will move outward one more time, as it always has, and the universe will be revealed to be, once again, larger and stranger and more astonishing than the last version of the map suggested.